So this week we are going to pick up where we left off last week and start going into our regression. So the first thing that I want to do, though, is make another variable. That's always what we have to do. And this is just to help us with interpretation a little bit. I'm going to have us convert the birth weight variable from grams to pounds. So we're going to go to transform, compute variable. Our target variable is going to be LBB weight, or pound birth weight, or whatever you want to call it. And then the numeric expression, we're going to move the birth weight variable over and multiply it by 0.0022. because that is the conversion rate between grams and pounds that I looked up. Everybody got it? 0.0022. So it's the new variable is B weight times 0.0022. Okay. Okay. And the first thing that we're going to do is just some basic bivariate regression, and we're going to look at how we get started with a variable of interest and your outcome variable. So the first thing that is always a good idea to do is to look at a scatter plot of your two main variables of interest. So we're going to go to graphs, chart builder, on this choose from left-hand gallery here, we're going to go to scatter dot, and then we're going to drag this first one called simple scatter into our window. The y-axis is going to be our new pound birth weight, and the x-axis is, we had talked about last week that probably a really important predictor of birth weight is gestational age, so the number of weeks until pregnancy. So we're going to use that one as our x-axis. And we're going to hit OK. So if we play the guess the correlation game, we can see that there's a pretty strong positive association between gestation in weeks and birth weight. But there is also, a fair amount of variation around that. So the next thing we can do is calculate what the correlation is. So we'll go to Analyze, Correlate, Bivariate, and we will put in there our pound birth weight and gestation. And press OK. So there we see we have a pretty strong positive correlation of 0.638. So that is going to be like your main primary way of describing the relationship between two variables is a correlation. But you can also do it as a regression with the same two variables. So let's regress it. We're going to go to Analyze, Regression, Linear. Our dependent variable is going to be our pound birth weight. And our independent variable is the gestation. Let me hit OK. Okay, so if we go down to our coefficients, we see that we have a beta coefficient of positive 0.29. So that interpretation of that is for every increase in 1 week of gestation, that's associated with a 0.29 pound increase in birth weight. And if you can see also there that that's different from our correlation coefficient, but the standardized beta is the same as our correlation coefficient. So if that's helpful for understanding what a standardized beta is it's putting your two variables in the same units and measuring their relationship to each other, whereas the unstandardized beta coefficient is in its original units. So another way that we can get this equation is by going back up to our scatter plot and double click on it to go into the chart editor. And go to Elements and click on Fit Line at Total. And we can here see all the same information that we just got from doing our regression. So it gives us this line for the equation for our line, which is negative 4.03 plus 0.29x. So, and we also get our R squared shown. Does everybody have that equation up here? Okay. Our R squared is shown as 0.048 or 408. So, where is Elements? It's in the chart editor. So you double click on your scatter plot and it should like launch a new window for the chart editor. Yeah. Okay. So that is our regression equation. That's the really important key interpretation of beta coefficients, is to get that regression equation. And what the regression equation does is that then you can put in whatever value for X and get your predicted average birth weight. So you would, well, we're going to go through the math of it in the next one. We're going to add another variable first. Okay, is everybody clear on that? Just basic two-variable regression. Run it, find the relationship between them, and you can interpret it as a line that's fit between the dots on the scatter plot. Now, that's the simplest way to understand it, as that line fitting the dots on the scatter plot. And then what happens when we add more variables is it's just like adding more. You can't draw the scatter plot anymore, but you can imagine like a three-dimensional space with all of these data points, and it's trying to fit the line that best hits the most of those data points. So that's what the regression calculation is doing. So let's add another one. So we're going to go to Analyze, Regression, Linear, and let's add what this whole thing is about. Does everybody have the smoke dummy that they created last time? Okay, well, we're going to add that to our regression. So put that in the independent variables in this block 1 and hit OK. All right, so we have the makings of a new equation. And if you look on the outline that I posted up on there, that's here, I have the basic formula of the equation is that you have your predicted value for your dependent variable is equal to your constant plus the beta coefficient times your independent variable, and so on. So when you have more than one, you multiply it and add it up by each of your independent variables. Oh wait, I did do it for the 2 first. Okay, so the line that we got in the last regression was negative 0.403 plus 0.29 x. So if we want to predict what the average baby birth weight is for a gestation that went to 40 weeks, we would just plug in the number 40 there for our weeks for gestation, and we'd get 5.75 pounds as the predicted value of that birth weight. So, of course, there's going to be a huge distribution. Well, may or may not be huge, but there's going to be a distribution for everybody who had their baby at 40 weeks that's not equal to 7.57 pounds. So this is just the predicted weight. It's the predicted mean weight. So it's for all of those people who it is. That it's different from what your output was. LBB weight. Oh yeah. Oh yes. That's the next one. Go. I backtracked. Yeah. Okay, so
this is for all. This is for all, not just non-smokers.
This is for everybody. Okay. Not controlling or taking into account smoking yet. Yes. Sorry about that. No, and then if we look at the weight, if we do the same thing at 41 weeks and plug it into the equation again, we get 7.86 pounds, which is, of course, a 0.29 pound difference, because 1 unit increase in weeks equals a 0.29 pound increase in birth weight. So that's just demonstrating, showing there how you can calculate that out and get those predicted values. And then also I have the interpretation written out in case you're looking for some language when you're writing up your findings. So it's written very clearly there. A 1 unit increase in weeks of gestation is associated with a 0.29 pound increase in birth weight. Now, that language of is associated with is really important, because sometimes it's easy to, what we try to do in doing a regression and controlling for all these variables is figure out what's causing the birth weight. But you can never use that language because we don't have an experimental design that's, or multiple time points or anything like that. We can just say that this is the association between the two variables. So is associated with is going to be a phrase you use a lot in your homework write-up. And the interpretation for the standardized beta is what you guys did more in the in-class lab, which was a 1 standard deviation increase in weeks is associated with a 0.68 standard deviation increase in birth weight. Now, when you're just looking at two variables, to me, that actually doesn't really mean anything to me. I feel much more confident that a 1 week increase is associated with this pound increase. So whether you want to use and how you want to use your standardized betas is going to depend on how many variables you have and how confusing or not it is to interpret them. Okay, so now we'll move on to adding our smoke dummy. So we got the output, and the the predicted line that we got was weight in pounds equals negative 0.83 plus 0.28 times gestation in weeks minus 0.41 times smoking. Now, if you recall, our dummy variables are organized as either 0 or 1. So if you want to predict a 40-week non-smoker birth weight, you would do negative 3.83 plus 0.28 times 40 minus 0.41 times 0. So you're not calculating that smoker variable. So it's still part of the equation, but it gets canceled out because you multiply it by 0. And you get 7.37 pounds. And if you do the same calculation for a 40 weeks birth for a smoker, then you do the negative 3.83 plus 0.28 times 40 minus 0.41 times 1. So we are going to subtract that 0.41 when we want to know what the predicted birth weight is for a smoker at 40 weeks. Yeah. When we added the new variable, it's because smoking is associated with gestation at weeks. So some of the variation that was being initially accounted for in calculating the relationship between smoking and weeks, or I mean between weeks and weight, some of that gets taken up by the smoking. So there is some independent of that is, so you can see that we are adding a little bit to our R squared. So we are explaining a little bit more of the association with weight, but some of the association between weeks and weight is also associated with smoking. It's the relationship between smoking and weeks that overlaps, that changes our beta coefficients. And that is generally true when you start adding more predictors, that and usually they'll go down. Like you'll see that they have a less strong impact. It is theoretically possible for it to go up if the relationship if it's controlling for something, then it can go up, but usually what you see is it goes down. Yeah.
If they just theoretically, if smoking and gestation
were not related at all, then you wouldn't see a change in your beta for gestation when you add it. But of course, everything's a little bit related. Yeah. 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 And so how we interpret the beta coefficient for a dummy variable is as the mean difference between smokers and non-smokers. So you're going to, and then also because we have another predictor in there, we have to say that we're holding it constant. So you can see the interpretation there. Therefore, holding weeks of gestation constant, status as a smoker is associated with a 0.41 pound reduction in birth weight. Smokers have a mean birth weight of 0.41 pounds less than non-smokers. So that's your interpretation for a dummy variable. Everybody got that? Oftentimes, when we're doing things that have more than just two categories, smoker and non-smoker, then we, like race, and we want to put a dummy in for Black and a dummy in for Latinos, then we leave one of them out. So we would, if we have white, Black, and Latino, we'd leave white out, and then the interpretation is the mean difference between whites and Blacks is your beta coefficient for your Black dummy. And then you have to run it a different way if you want to see what the mean difference is between Blacks and Latinos. So I don't know if we're going to get into all that, but it can be done, and the dummy variable interpretation is mean difference. It's not because a 1 unit change doesn't mean anything. So that's why it's a different language that you use for that interpretation. And then your interpretation for your weeks of gestation for that same regression is the same, only you add that you are controlling for smoking. That holding smoking status constant, a 1 unit increase in weeks of gestation is associated with a 0.28 pound increase in birth weight. And we can see that there is a slight increase in our R squared when we add these variables. Whether that's significant was something that I was going to show you, but I'm not now. But if you're curious, we can look at it later. Okay, so let's add another variable. Let's add in our mother's education. And so what we can do is, another thing that you may want to do as you're comparing these different models is to do your regression in blocks so that you can see all of those different models when you added those variables together in the same output. So we're going to do it that way. So we're going to go to Analyze Regression Linear. We're going to take our smoke dummy out of the first block and then click Next. Then we're going to add our smoke dummy there. Click Next, and we're going to have a third block where we put in mother's education. Does everybody see where you can change those blocks? Okay. Yeah. So your first block is going to be gestation. You're still going to have the same dependent variable of, and then you hit just Next there, and then you put in the smoke dummy, then Next, then education. Okay. So the first thing that we see here is that we do have an increase in our R squared every single time we add a new variable, but the increase for when we add mother's education was bigger for when we added smoking. So we can see that that's having a bit more explanatory power than smoking did. And we can also see that when we look at the coefficients. So, so when we first started, we had our gestation was 0.29. Then it went down to 0.28, basically 0.29. And then now in the third, when we add the mother's education, which is also associated with weeks in gestation, it goes down again to 0.26 or 7. Our smoking mean difference coefficient also went down from negative 0.41 to negative 0.27. And we see that our coefficient for education, mother's education in years is 0.09. So each of these, if you look at the significance on the far right column, is a significant predictor. So we can be confident that each of these makes a difference in determining the weight of the baby. If you have a coefficient that's not significant, that just means that we can't say that there's an association between this variable and our outcome variable. Yeah, I think so. Then when we start adding more variables in, even though when we just had one and our dummy, the clearest way to make comparisons between them was by looking at it directly, looking at the unstandardized beta. But when you start adding more different variables in, the standardized beta coefficient becomes a better, more useful metric to have. So we can see here that our standardized beta gives us information about the relative predictive power of each of these variables. So we can see that clearly the one with the strongest relationship with weeks of gestation, with birth weight is weeks of gestation, with standardized beta of 0.59. So the interpretation of this is that holding smoking and mother's education constant, a 1 standard deviation increase in weeks of gestation is associated with a 0.59 standard deviation increase in birth weight, in pounds of birth weight. And we can see that this is much higher than our standardized betas for education, which is only 0.19, and smoking, which is only negative 0.07. So while smoking is still a significant predictor, has significant predictive power in determining the birth weight of a baby, once you start controlling for things like gestation and education, it is not as strong a predictor of birth weight as these other variables. Now, what does get tricky is when you try to what's good about interpreting standardized beta coefficients is that you can compare them against each other in the same units of standard deviations, rather than, you can't really make much meaning out of the differences because in the unstandardized betas, because they're in different units. You can draw some conclusions if some are more or less significant than others. You can, that is associated with being as good a predictor, but it does not indicate what the effect size is, like how much variance is accounted in our dependent variable is accounted for by our independent variable. And that's what the standardized beta coefficient does. But to directly state, to try and use that standard deviation interpretation on a dummy variable doesn't actually make sense, because there is no standard deviation increase in smoking, because you're just either a smoker or you're not. So so whenever you have dummy variables, you're going to want to stick with interpretations of your unstandardized beta and talk about the mean difference in real terms, because those are the units of your unstandardized betas for dummy variables are in pounds, or whatever the units of your y are. And well, all the betas are in the pound units, but the problem is that how many x units it takes to account for that amount of increase is what's different between the independent variables.
So does that mean that when you're looking at the standardized coefficients,
Mm-hmm.
does that mean that, for example, in the third,
Yep. Mm-hmm.
this looking at the negative 0.71,
Mm-hmm.
does that mean that's not, what does that mean? Does that mean that's not very, where's that come from? Not very helpful.
It means that it doesn't have as much predictive power as the other two variables. That it's not as strongly associated with birth weight as the other predictors.
Because it's lower.
Yes. But it still is significant. So you can say it's a significant finding with a small effect size.
I'm trying to understand why you said that we should use the unstandardized data. I mean, I understand the logic, but then I was trying to understand it based on these numbers.
It's because you can't say that there's a mean difference between smokers and non-smokers of negative point, well, I guess you could say of negative 0.07 standard deviations of, but no, you can't say it's a mean difference because it's a 1 standard deviation increase in smoking, which doesn't mean anything.
Right.
Because it's only 0 or 1.
Okay. So, but we can still use that number to compare it to.
Yes. So you can use it as comparison, but you can't use it to say anything. Yeah, you can't use it to say anything about, you can use it to say something about how well it predicts birth weight compared to your other things. But if you want to say something about the birth weight of smokers and non-smokers, you have to use the unstandardized.
Okay.
Yeah.
Because if you compare the 0.589 to the negative 0.74, that's not an accurate comparison. If you compare the gestation to the standardized coefficient for gestation to the unstandardized data for smoking.
No, that doesn't work either.
Okay, okay, thank you.
No. So it has to be like it's basically, it's answering two different questions. You put a dummy variable in there to answer the question of what is the difference between these two groups. And you look at standardized coefficients to answer the question, what is the effect size or predictive power of these different variables? Okay, so those were the regressions that I plan to run. Are there any additional questions? Would you like me to go a little bit deeper into any of these things? If you've looked at your homework, what things in there are confusing or do you need help on?